right, I'll do my best to not bore you here. There's a bunch of slides, and I will be going through them. I'll try to go through them fairly quickly. I know lunchtime is pending. So anyways, basically we're going to talk about some of the architecture, where our company started and where it's been, kind of where it's going. I know Josh touched on some of that, but I'm going to be talking more sort of, well, you'll see. We're going to talk about Kafka a bit more, some patterns, Q&A. I got to do a shout out to Confluent. They're one of our partners, and I am using a lot of their slide content. Basically, they have a number of much more in-depth slides that explain all this really well. So instead of reinventing the wheel, I'm using some of their content with my own content to glue together some specific topics. So this is, when you see these white slides, these are the Confluent ones. Mine look like very traditional PowerPoint ones. But basically, so this is where a lot of companies start. This is where Flipp started. You're an internet-facing company. We were doing comparison shopping way back when. And what you end up with generally is some sort of front-facing website. You have glue code, in our case Ruby, on Rails. And then you have a database in the back end that's handling a lot of these requests. So this is good. It's quick. It's easy. You start up quick. You get your services out, and you start trying to make some money. So as time goes on, each one of these little circles here could also be thought of as a service, probably with its own blue box and its own database. But you carve pieces off, you end up building out your services. But then you realize, okay, well, if we're going to add, let's say we want to add coupons, but we want to add them alongside of products that appear in our flyers, then we need to get this data from this system over here and put it in this system. So you start having meetings with whiteboards, and you start drawing these arrows, and you start hooking things together, and you go, okay, well, you know, this will work. Like, you can get this in here, this isn't a problem. But generally, once you draw that arrow and then you go implement it, that arrow's not going away. So every time you add something new, you get a little more complexity, a little more complexity, a little more complexity. Also, one of the, let's say, what's it saying there? It's a double-edged sword. If you have like a nice Ruby on Rails database system, it's really easy just to add stuff in there. So like, yeah, sure, your service was built around flyers, but like, you can just put this other stuff in there too. Because like, it's really easy, and you can just add this, and you can add this. And the thing is, you're going to make your deadlines, you're going to get your products out, and it's not that it's a bad thing, but you're starting to rack up technical debt on your technical debt credit card. And yes, this will come back, and you will have to pay for it later. So as a startup, I get why you're going to do this. You're worried more about now, you're worried more about the present, you're worried about getting your product out the door, you're not worried about what's going to happen in 3 or 4 years. So yeah, these services might use a database, they might share one, sorry, like this guy was doing. Shared databases become a nightmare, or they might use their own. But then what you end up with at this point is you now have data that's fully encapsulated within services. And if another service needs that data, it's going to have to figure out a way to get it. And you end up with something like this. So your various services end up having APIs to talk to other services to get certain data from them. But like maybe, you know, the red systems need a certain API and the yellow systems need a different API, but they're very similar, but they're kind of different. And you get a bunch of complexity. And so this is where things start to become very difficult. And you go, well, what do we do about this? You also have other issues, such as buffering, handling failure back pressure. So if one particular node fails in this diagram, a node, I guess, being a service, you know, how does this affect other services? Like, do they have blocking REST calls, or do they not? Do they, like, can like a new system that's brought up have a chain reaction effect that will bring down other systems? And generally, as you grow bigger and bigger, it's impossible for anyone at the company to really know what's going to happen when you have all these different systems all tied together, and you start building up a significant amount of risk. It also makes changes really hard to do, because you're not really sure how bad of an effect a change may have. So you get these sort of tight point-to-point couplings. And I wouldn't say Flipp got to be as bad as this, but I don't even want to say that this is bad. This is natural. This is where you're going to go, no matter what kind of company you are, unless you do things differently, either right from the start, which may not merit it as a startup, but eventually you're going to have to come to a point and you're going to have to decide, okay, are we going to keep doing this? because the short term, it's easier to keep doing it. The long-term risk gets higher and higher. And as you go further in time, that technical debt will come and bite you. Just for interest's sake, I used to work at BlackBerry, worked there for 4 years. That is a company that's technical debt bit it in the ass hard. So I will freely say that, and I know firsthand what the impacts will be if you keep pushing stuff off to the future. So anyways, you get these type point-to-point couplings. Let's look at a different way to do this. So event-driven architectures. These are, I don't know, have anyone of you heard about those before? Yeah, so event-driven is essentially, instead of having like, you make a request for something and you get something back, you start sort of communicating via messages or events. That being said, there's still two ways that you can do this. You can have services that are directly coupled still, interacting through events, or you can decouple all the services and use a different sort of system. So I'll get to that in a sec. So this is a really good example. So simple payment service. It's a magical little blue circle. So basically what you're going to get in this thing is you're going to have purchase request events coming in, and you're either going to make a payment or fail a payment. It's not really keeping any state in there, and any state that it does keep, sorry, let me rephrase that. It's probably not keeping any state in there. It's probably going to be communicating with like a bank's endpoint or like Moneris or I don't know, some sort of financial endpoint saying like this is the payment, this is the person's details, here's their credit card, pay, and then it's either going to succeed or fail. And based on whether it succeeds or fails, it's going to publish a message back out. But the important thing here is that this service, while it owns the data that's coming out, it doesn't keep it encapsulated. And you don't have this. So you don't have a service that communicates to a payment service, and the payment service is the only thing that can access that data, because then you have that tight coupling and you have that, that direct API. So it's a subtle sort of difference, but one that unlocks a ton of potential. So I could actually probably talk for like a solid hour or like two on what Kafka is and how Kafka works. I'm going to gloss over a lot of the detail. But essentially, it's a Apache open source distributed message broker system. The fundamental unit of data is called a topic, and a topic is basically a message queue. But I really hesitate to use the word message queue because most traditional queuing solutions, you put a message in, you read it, and it's gone. That's not how Kafka works. With Kafka, any particular topic will have a single message type. So in our particular case at Flipp, we'll have things like item click. So you've clicked on an item, in your Flipp app, or you've opened a flyer. So like a specific event that details some user behavior. And those will be contained with, like each one would be contained within their own topic. So if you have 300 or 400 different behavior events, you'll have 300 or 400 different behavior topics that you can listen to. The data is produced via a series of we basically get data from the device as people are engaging in stuff, and we'll produce that into our cluster, and then the consumers would be anybody that wants to register on that. So a really good example would be like real-time billing. So some of our merchant partners will pay for, it's called our premium service, they'll pay for promotion. So we will promote their product, but when we drive additional traffic to them, then they pay us for how much traffic we get. So one of the big differences about Kafka is that you have data persistence. So you can keep your message in your queues from like as little as 1 millisecond, which would be totally useless, to infinite, so never delete it. So what this actually is doing, if any of you are really familiar with like regular old HDFS, HDFS is the underlying big data Hadoop file system. So that's batch, like lots of batch file system, but you can keep all your data there and you can keep it for as long as you want. This is sort of like the real-time equivalent of that. So they're moving into a space where you can store all your events in real time as they come in, and you can persist them for 1 millisecond, 30 days, 30 years, however long you want. You're obviously going to need the disk space, but it works very, very similarly under the hood. So what this lets you do is it lets you register individual consumer groups. So in this case here, we would have a payment group, and the payment service would consume the purchase requested events and produce the payment completed and payment failed events. So really it becomes a microservice powerhouse. You get the Avro schemas. So this is another thing I could talk for quite a while about, but basically what Kafka is the message bus. It's synonymous almost to like a data bus in a CPU. All the data ends up on that bus at one point or another, and the systems will talk through the bus. Avro is the format of the data that you pass between there. So Josh mentioned in his presentation that we were having trouble with like freely typed strings because there's no sort of enforcement on that. So what Avro will do is it'll enforce a type on the data. So you would say like this field's Boolean. So if you try to put the number 1 in, it's not going to let you do that because it's not really Boolean. You have to type true. So essentially what it does is it provides you with a contract. And that's the operative word there, a strongly typed data contract. So you don't even need to know what the content of any given message is aside from the contract. And that Avro format, think about it exactly as you would the metadata header of a database table. It's pretty much exactly the same thing. You got defaults, you got strongly enforced types, and you can change it and evolve it through time through a series of what you call like compatible operations. So like adding a column, that's supported. Adding a default, that's supported. If you change a field type from integer to Boolean, that's not supported because all of your data in that table is currently an integer, so you're going to have to convert all that data over. So if you think about it exactly as you would like a database table, you're really on the right road to understanding how these services will communicate. So back to the Confluence slides. Just give me a sec here. So this is your traditional REST request response example. You got a payment process. You know, this guy on the left here, you know, is on Amazon or whatever. He buys something. It goes to the payment service. The payment service then contacts the payment provider, whether that's internal or external is, you know, its own detail. And then from there, it talks to the stock service and maybe gets more stock. And then from there, the stock service would probably inform a fulfillment service and so on and so on. But every single one of these double-headed arrows here is a specific API. And the downside here, obviously, is that you got to maintain all that. So the event-driven way goes to sort of that sort of CPU bus service. So in this case, the UI, you will listen to, or sorry, the UI service, this would be like a REST system that the user's interacting with. They will raise like, I want to buy this, right? So that user generates an event, and that event is real representative behavior of what's going on in the world. Like, so this will come into your topic for purchase requests. So there's a specific purchase request topic. The payment service listens to that, and it says, okay, I got a purchase request, so now we're going to need payment. So if you're using, okay, by the way, I got to tell you, I'm not a web dev, so I'm going to be making stuff up just to suit how I think the web should work. So the payment service probably goes, oh, okay, well now I got to ask this guy for payment. So whether it goes through a website or sends him an email or whatever, that's the payment service responsibility. The UI service doesn't care, and the stock service doesn't care what the payment service does. So all of the app logic is fully encapsulated there. The only thing the stock service cares about is if the payment is processed. So the stock service will listen to the payment processed event and any event. It doesn't care if it's in order, out of order. It doesn't care about anything except processing payment processed events. That's the only thing it cares about. It doesn't care about any other context or anything like that. And so based on that data contract it has, it listens to those events, it does its job, and then it'll either produce events back to the Kafka topic. And in this case, it would probably say like product shipped or product fulfilled or something, or like stock available. And then it would reserve that stock, and then there would probably be like a fulfillment service that would do the actual shipping. So all of these events basically all of these services tap off the events, do something with it, and then put them back in. So that's so this is a pure event-driven service. There's no talking between services at all except through messages of events. So one of the things here, like I mentioned earlier, the stock service will entirely own its flow control. So any changes to the payment service, we don't care about. They don't have to maintain an API. The only thing they have to do is respect the data contract. If they have to make a change, this is where Avro comes in. as long as they make a change that's what we call evolutionarily compatible, so sort of like adding a column or something like that, it won't have a negative impact on any of the downstream services. If you have to publish a breaking change, it becomes a little trickier. You can still accommodate those, but now you do need to talk to the stock service because you're breaking the contract, so you need to renegotiate that data contract. So this is obviously very different than the synchronous model because the stock service here is directly coupled to the payment service. So if the stock service needs to do anything different, it needs to renegotiate its API every single time it makes a change. It doesn't just have whatever data is available in that contract to use. Now, one of the very, very, very powerful things about this is that all your events become an immutable narrative of everything that's gone on in your entire system. So this is the equivalent of taking your data that drives your events and your logs and combining it into a permanent narrative. So you'll be able to actually troubleshoot all your systems much, much easier. You don't have to like start digging through log data and being like, okay, well, I mean, you'd still want to take log data for like, you know, any sort of like internal warnings or something, stuff you won't publish, but it's very specific to your app logic. But you'll be able to say like, okay, I know this event went into the system, but then nothing came out. But something should have come out. So we know the problem is in this service right here. So you can actually very easily trace your data through your system, figure out where things worked and where things didn't work, and you can start digging into the services a lot easier. And because the sort of approach you take to solving these problems is the same, because all these services are basically operating, like their app logic is different, but they're all operating in the same way, right? They're reading events and they're publishing events. The troubleshooting that you do for one service is very easily applied to other services. So it actually, app logic aside, it makes interchangeable, like you can bring extra people in to help build up services or like look at certain problems. So it makes your team a little more flexible itself as well. So like, yeah, services are coupled only to data flows. So there's no knowledge of the contributing services. We only care about the contract. And because the coupling is only to events and not services, you can do things like this and just drop in, you know, additional services. So a fraud service here would probably listen to payment requested events and payment made events, I guess. I mean, I'm not a fraud specialist. I don't know what you'd be looking for. But basically by adding the fraud service, if you don't need any new data produced by anybody, you can just add your service right in, and then you can start adding data into the system that other services may then build upon in turn. So the communication and state concepts merge. Data and events become one, but also Kafka becomes the event store and the communication channel and provides an immutable log of all the things that are occurring inside your system. So you get this, like I said, the canonical shared narrative. You get your orders, your shipments, your customers, your payments. And as your system evolves over time, you'll get additional, you can add additional columns, topics, and additional data. So this is the perfect world where everything works really awesome and great. Obviously, there's a few things that you have to be concerned about, but I'll cover those nitty-gritty details shortly after this part. The other nice thing is that scaling is entirely now a concern of the broker, with a nice little star there. So for any of your data load, like any of the reading or writing of data, basically what Kafka does is it's a very, very efficient message broker, and the broker will store the data on disk and replicate it, much like HDFS, but it also caches a lot of it, and there's like specific caching algorithms you can use. So most of the time you'll end up saturating either your network connection, actually it's usually network connection first, followed by hard drive second. So if you're finding that your brokers are lagging behind, you actually just add more brokers, and then you can either increase your replication across the different nodes so you can serve all your data much quicker, or sorry, with much larger bandwidth. The latency will be about the same. Or you can sort of tweak basically your distribution of your topics and do all sorts of other neat things to improve your performance based upon your usage patterns. The only thing you'll need to do is scale your microservices up. Let's say you read 100 messages, and by the time the next 100 messages are ready, you've only processed 10. probably need to increase your processing by at least a factor of 10. So you would probably scale out your microservice, but you can read all of this data in parallel. You don't just have like one node pumping through everything. You can actually have 10 nodes, 20 nodes, 30 nodes, and they will all be able to work on a specific slice of that data on their own. So you go from something that looks like this, which is all your directly coupled microservices. You have shared databases, different services writing into databases, reading from databases, talking to other databases, et cetera, to something that, well, okay. So anyways, Kafka's supposed to be at the bottom. I don't know why it's not. Yeah, so right where all those little yellow lines are pointing at the bottom, it should actually have this nice little rectangle that says Kafka Data Brokers. But essentially, all your systems will strictly talk through, and I know I keep repeating myself, but this is very, very important. They only talk to the brokers. They don't talk to each other directly. Oh, there it is. Okay, all right. Oh, there you go. And inside of the broker, though, you're going to, oh, I know what's going to happen on this one. Yeah, it's going to do that. Okay. So inside of the broker, though, you might see topics that look like this. So you can vary how long you keep stuff. So flyer item clicks, we get a lot of those. And we're mostly only concerned about the most recent ones. So we have long-term durable backup on S3 for all of our data. But we don't need to keep like 2 years of flyer item clicks in that topic. If we're billing on people clicking on our flyers, which we do, we bill on something. Anyways, we only need maybe like 30 days worth tops. And that would be like, so people are generating probably, ideally, a streaming event that processes the billing in real time. But maybe for some reason we have there's a bug in one of the app logic and we have to go back and reprocess this, no problem. We just drag the offset, which is so every application will have its own offset in the topics, saying like, I've read from here and I have this other data left to read. So you can actually reverse it in time and then you let it go and it just goes back to the end. So you can choose to where you want to rewind your data to and then play it all back. So obviously this means that you need to be wary about your system design. So if you're doing bill payments and you wind it back in time, you don't want to rebill everybody again, right? So you need to make sure that your stuff is either idempotent or you have maybe like unique hashes for transactions to ensure that if you're going to redistribute these, that the downstream service knows not to send ones that it's already sent before, et cetera. So things like flyer entities, though, we may keep for like 18 months. So this is like the actual flyer itself. And the reason why we would probably do more than a year is because we do a lot of seasonal stuff. So with Black Friday coming up, there's a very good chance that we're going to be looking at data analysis patterns from last Black Friday. So we could even do something like real-time comparison between last Black Friday's data and this Black Friday's data as it comes in. Merchant entities, we would keep these forever. So if we onboarded Walmart 4 years ago, well, I still want it in my topic because I will be reading data from there, and if we add new merchants, I want to get those as well. And just as an illustration of like the payments, because if you're dealing with financial data, you will be audited at some point, and you're going to keep everything. So we could keep it all in Kafka, assuming this was our only data store. We could also roll some of this out and put it into S3 if we want, but assuming this is our only data store, this is what we would do. And then obviously you could have many, many, many more topics. So in summary, the really important stuff is you get to decouple your system. And with that decoupling, you get a total canonical record of events. The data duplication issues go away. I didn't really touch on those, but basically if you have shared databases, if you have databases that generally need the same information and it's in one database but another one needs it, the 101 is you just copy it into the new database. Now you have 2 copies, right? And then maybe you don't really copy it all the time, so now you have sort of what we call 2 sources of truth, or 1 source of truth and 1 source of like nearly true. And then you'd have people generating reports off of both of them, and then they go to the same person and they say, hey, these aren't the same, why aren't these the same? And then you get to spend like a couple of weeks figuring out like why is this data out of sync with that data, and then just trying to figure out like who else was affected by this, and basically at the end of the day it becomes a really bad idea. So don't duplicate your data. Kafka will stop you from doing that. You get to decompose existing systems into microservices. So we can take some of those monoliths that we've built, obviously not all overnight, but we can start splitting pieces off of them. And we can, well, first step would be, and this is what we're already doing, is building the new services off the monolith. And then the next step would be taking the low-hanging fruit from the monolith service and start splitting those out into services, so then you can further decouple it. Our QA guys love this. It makes everything way, way easier. They can monitor the actual events themselves to see how things work, like data going in, data coming out, is everything working? And this makes integration testing way, way easier. If every single service you write has the same sort of interface, and every single service you write only needs to be concerned about the data contract, as long as you're following that contract, you're good. So we're almost at the end here. There's two patterns that are important. Because this is Apache, and well, sorry, not just Apache. Because this falls under like the big data world, everything's in Java. Like the brokers are in Java, all of Kafka's in Java. All of the really nice libraries of Kafka are in Java. So there's also non-Java support, a lot of non-Java support I have to add. But there's a few specific patterns that will help illustrate what we're doing here. So I'm just going to touch on one of the Java one. Okay, well I'm going to touch on a Java one and then a not Java one. So the stateless processor, you can do this with anything. You could do this with Ruby, Node. You can do this with Java, Python, whatever other client support. But basically all you're doing is you're reading the purple stream, you're doing something on the event, and you're outputting the orange stream. So maybe you are simply making a neat little dashboard that shows engagement by geographical region. And you can see like which people are using Flipp at what time. You know, if you showed a whole map of the United States and Canada, you would see this ripple going east to west right around noon. People love to look at it at lunch. So you would see like sort of like this heat map sort of ripple across the United States and Canada. And like some cities were much more popular than others, so they would really light up and other ones wouldn't. So a stateless processor can do this for you. Now, this slide, so when I said I could talk about Kafka for a very long time, this slide sort of brings together a lot of concepts, some that I haven't introduced to you. But one of the things that the Kafka Java library gives you is the ability to take a stream of data, an Avro encoded stream of data, and not basically, but almost, sorry, yeah, it lets you take the stream of data and turn it into a database table in your app. So you can't run, okay, let me rephrase that. You can't yet run arbitrary SQL on it. That's something that Kafka is actually working on right now. But what you can do is you can take the table, and so let's say we had those merchants from Flipp. You know, we added Walmart 4 years ago, let's say. So I want to manifest, or sorry, it's called materializing. I want to materialize the merchants into a table. And I want to materialize the flyers into a table. So these are what they call K-tables. This one's called a global K-table. The global K-table is just a total copy of the data on each. So if you have one node, it's all in one node. If you have two nodes, it's in both nodes, like the entire copy. So what you could do with the Java one is you could materialize these tables on the fly. So you don't have to manage a database. You just actually say like create table, read this topic. And then you get a stream of events. You can join those events on the merchants and say like, okay, we're going to be billing these merchants for these flyers and we're going to bill them this much. And everything exists strictly within your application. If the application dies, no problem. You just fire it back up again, it rebuilds the table, and away it goes. So you don't even have to manage a database, but you get the power of joining streams on databases all built within the Java, the JVM. So I'm a big fan of this. We've done this. It works incredibly well. There are some performance considerations. If you try to materialize a table with 100 million 100 million events, it's going to take a while. So you need to know what your usage patterns are, and you need to, obviously pay attention to how you're going to store that data. That being said, it wouldn't be quite fair. Much of our company is based on Ruby and Node. So in Ruby and Node, we don't have the ability to use global K-tables or K-tables. Maybe in the future, someone will, write a libraries that support that, but we don't have that ability. So we need to support Node and Ruby as well. And so to do that, we use this, yeah, you can totally ignore the numbers at the top. But anyways, this is called an external database, which is pretty, obviously, it's an external database. So here we have the Kafka brokers, that nice purple rectangle. And we use it's a producer and a consumer rolled into one. This is open source, the Kafka Connect system. You get it when you get regular Kafka. And essentially what we're going to do is we are making a regular old database, a MySQL database. Now, we do a lot of our stuff in AWS. So if we want a database, one of the very easy solutions to use is Aurora database, because it's MySQL, the JDBC drivers work, and we can basically just pour money into it and the performance goes up. So it's easy to maintain that. Now the fraud service in this case would be, say, Node or JavaScript. Or sorry, the same thing. It would either be like Node or Ruby, let's say. And that will be able to connect directly to the database to materialize and perform any relational stuff that it needs to on the database. So the pattern here becomes a bit more complicated, but what we're doing as a company is we're taking that whole thing and we're Dockerizing it. So we're providing this as a service in conjunction with our microservices team to basically abstract away the Kafka Connect APIs, make the database setup very easy, which already is pretty easy, and give them a framework to say, okay, this is where you build your app and you're going to connect to this database. Now, what their responsibility is, it does show an arrow coming from the Kafka cluster going straight to the fraud service, but there should also be, in my opinion, an arrow going from the fraud service back to the Kafka cluster. So if it detects any fraud, whether it's validating or refuting, payments are valid or payments are not valid, it will need to reproduce its events back to the back to the Kafka cluster and not to its external database. The whole point of the external database is strictly to be a waypoint for the data so they can perform their relational queries on it. That's it. Technically, arguably, it should be read-only, but if they need to maintain state, they could use that database to maintain their own state within it. So the pattern is basically dump the data into the database, tell them don't store any data in there that you want to share, because this becomes a violation of the entire principles that we've set up, and you need to publish your data back to Kafka. So as long as they do that, that's what that context boundary sort of line is. We can black box the whole thing, and whether it's a Node or Ruby system, or whether it's a Java system, it's almost totally irrelevant. As long as the maintenance of the data contract remains the same, that's the only thing we care about. I'm just going to skip this. I meant to delete it. So questions?
First of all, thank you for your clear presentation. I really enjoyed it.
Thanks.
I have a question regarding those microservices that are really tightly coupled.
Yeah.
And what if they need to
Like something like that?
send messages back and forth a lot?
Right.
So in this case, they have to talk with each other through Kafka, right?
Yeah. So.
How's the performance?
Okay, so here's the question is essentially, let's say you have existing directly coupled microservices that do a lot of communication between each other, right? So the answer to that is, this is a perfect world. That's probably the real world, and we're going to end up somewhere in between. So you don't have to have, it's not an all or nothing proposition. If you do have existing systems that are directly coupled and they provide a lot of communication between each other, you know what? If it works and you're not having a lot of pain points around it, leave it alone. Because it ain't, if it's not broken, don't try to fix that. And that approach is called a hybrid approach. And essentially, if performance is very, very important, where this has to be able to reply within a certain amount of time, then you can definitely keep your microservices directly coupled like that, provided you have very specific specific SLAs around it. There's nothing wrong with that. The only issues that kind of rise come when you have many directly coupled ones with a lot of a lot of data that's all sort of like mashed in together. So it depends, but there's nothing wrong with doing that to keep those services as they are. If you do want to talk to services between, like directly between in Kafka, the latency is not going to be like sub 10 millisecond, but it's not going to be like 500 millisecond either. It'll vary. So there's certain things, like obviously having your data, your servers co-located within like the same data center is obviously going to be a big factor. But Kafka, by and large, is really, really fast because any of the really important data that you need to do at high speed, you can basically just say like keep these topics in RAM, and like as soon as it's written, it's readable, and like we're talking, you know, whatever, like pretty quick, like sub 100 millisecond sort of things. The thing is though, it's still going to be technically asynchronous. So if you want your client to block and wait for a response or not, that's going to have to be part of your design.
And considering these event-driven microservices, how do you scale them? We know that Kafka has back pressure,
Right.
but you're like client-facing application.
Right, so if you have a client-facing application, so it depends on if your load is coming from too much Kafka data or too much client data.
And let me give you a scenario.
Okay.
I'm doing credit card transaction. It's transactional data.
Right,
It's coming to you, it's go to Kafka, and you have a service in the back, and you have burst of input. How
Right.
do you scale that microservice?
okay, so if you have a lot of data coming from, like bursty data, like let's say payments, right? You know, maybe people are buying a lot of stuff in the evenings, but then nothing overnight. So how do you scale your systems according to that? So in this case, it would be, so I'll put it this way, Kafka is not great at dynamically scaling. They are making things better, but basically you would want your Kafka data backbone to be able to support your worst case scenarios.
No, let's assume Kafka support that, but your microservice.
Okay, for the microservices then, what you would, okay, so what we're gonna do, what we're doing as a company, is we're using, so I build my microservice, it goes in a Docker shell, and that is hosted in ECS, which is Amazon's Elastic Cloud Service. And we hook up our monitoring on the load balancer and on various like CPU memory signals, such that if we cross a threshold, we increase the number of tasks. So we would increase the number of tasks, we would bring up another service, it registers with the Elastic Load Balancer, and now it's going to take on some of the new load coming in.
Yeah, but Kafka doesn't support one and only one delivery. So you're
It does now. As of 0.11, it does.
Okay.
Yeah.
So now you're saying.
Well, it depends, because your system as a whole should be able to handle duplicate records. Because if you want to be able to replay stuff, it would be wise to have the ability to have duplicate records. Because we're not handling most payment info right now, we can kind of punt that down the road. That being said, you guys are all familiar with Capital One. So Capital One is like an industry leader of banking, but also of technology. So I went to the Kafka conference last week. Capital One gave a presentation where they're doing exactly what you said. They're taking credit card payments and they're processing it through Kafka using auto-scaling and all of that. So they're doing it, it's in production, and they're very satisfied. They're not revealing all of their secret sauce for the competitive edge, but it's doable.
Okay.
And the real question that someone had for them, though, was how do you know you've missed a transaction? Not that you've gotten two, but that you've missed one. And that is still a problem that, it's sort of like they promise like 99.99% uptime. They're going to get most of the payments.
Yeah.
But if you miss one, that can still happen.
They are good, I think.
So they're good, but they're not perfect yet. So there are some sort of corner cases where, and that's why it would be better to like be like, if you're not sure, send it again. Right? You're better off to have two messages than miss it altogether. So I hope that helped.
Yeah.
Okay. Anybody else? All right, cool. So just to continually stress this, I personally think that this Kafka data backbone, I think they're onto something very, very big. Like this is, I believe, is going to change the way a lot of companies build their business applications, because it gives so much additional power and so much additional flexibility that to not do it this way is going to be fatal in the long run for a lot of competitors' abilities to meet sort of like the changing business requirements of their business. So if you don't know anything about Kafka, I would recommend going to the Confluent site. So Confluent is they're the guys that started Kafka when they were at LinkedIn, I think it was. Yeah, LinkedIn. And then they made their own company, and they're basically providing like enterprise and professional services. But they also do a lot of the open source development, driving, and like bug fixing and stuff. So they're sort of the stewards of it, we'd call them. But they have some amazing documentation, some really amazing videos that go further into detail. You'll probably see some of the slides that I showed you in some of those. And honestly, I personally think that this is a very like important topic to look at. So anyways, thanks for listening. And I don't know what to do now. Do I give it back to you? Is it lunchtime?